Welcome back, everyone, to our continued discussion of the theory and intuition behind random forest. Let's begin focusing on hyperparameters specific to a random forest, beginning with the number of estimators and number of features. Recall that when we're discussing the number of estimators to choose for a random forest, we're really trying to answer the question, how many decision trees to use in total for that random forest? When we're talking about the number of features to choose, we're trying to answer the question, how many features out of the total n number of features should we include in each subset to be randomly selected for each potential split? Let's begin by discussing the number of estimators. Now, intuitively, we know the more decision trees, that is the more number of estimators we have in the total random forest, then the more opportunities to learn from a variety of feature subset combinations. We already know that each decision tree, based off that random subselection, is going to look different than previous decision trees. However, we want to understand the question, is there a limit to adding more trees? And is there a potential danger of overfitting if we create too many estimators, that is, too many decision trees for our random forest? Well, here's where we can actually take a look at the creator of random forest, Leo Breiman's official page on random forest. And he quotes, "Random forest does not overfit. You can run as many trees as you want. It is fast." So 3 very simple sentences, but very powerful remarks that you can see on the official page for random forest. Now, what does Leo Breiman actually mean when he says it cannot overfit? Let's think about this. So, if we take a look at previous research on trying to decide the number of trees, then you'll notice there's a theme where a reasonable default value is 100. And in many publications where empirical tests were done, suggests somewhere between 64 and 128 trees is a good choice to make. Obviously, this will depend on the number of features you have in your data set. The more features you have, then the more trees that are going to be useful in revealing information from those features. A quick way to actually decide on how to choose the number of trees is to cross-validate a grid search of trees. Start with some reasonable default value like 100, and then maybe go a little less and a little more, perform a grid search, and then compare the best performance for the best number of estimators. What is also a popular tactic is to plot error versus number of trees. This should feel familiar because it's quite similar to the elbow method in k-nearest neighbors. What we should notice is we get a diminishing error reduction after some n trees. And this is where we're going to tie back in to Breiman's statement that it cannot overfit or doesn't overfit. And why is that so? Well, let's imagine that we were going to test out multiple random forest model where we decided to increase the number of estimators. You can imagine that the minimum number of estimators would be 1 decision tree. So this is actually weaker than a normal decision tree, because recall, we're only going to be selecting a random subset of those features. So if we had a single decision tree in the random forest, we would expect to have a high error. And then as we introduce more estimators, that is decision trees, we should expect to get a reduction in error because we have more features available and different trees that will hopefully learn better on that data. And eventually, if you were to plot this out, you would see a behavior that looks like this. As you increase the number of estimators, your error is going to get reduced. But after a certain number of estimators, you're eventually going to reach some sort of threshold in error, regardless of how many more decision trees you add. But you should also notice that it doesn't begin to spike up after adding too many trees. It essentially just hits this limit of error. And why is that so? A simple way to try to understand the intuition behind Breiman's statement that the random forest does not overfit is to imagine an extreme example where instead of using the published recommendations of something between 64 and 128 trees that were empirically solved for, instead we decide to go huge, like 5,000 or 10,000 trees, really pushing those limits. Well, what would occur? We can imagine that after a certain number of trees, 2 things are going to begin to occur. One is that different random selections are not going to reveal any more information. That is to say that eventually new trees become highly correlated to previously built out trees. That means tree number 1 ends up producing the exact same prediction outputs as tree number 100 or number 1000. And really, because these trees are becoming highly correlated, it doesn't mean that you're actually overfitting to the historical training data. Instead, you're basically just producing a duplicate or highly correlated prediction, which is to say that that other randomly selected subset that built out a decision tree isn't revealing any more predictive information from the features. We could expand this idea to some extreme amount of decision trees to realize that different random selections are simply duplicating trees that have already been created. Now, we would have to go to a quite large value of the number of estimators in order to begin to duplicate decision trees, but hopefully you can see that is definitely possible given the fact that there's only so many different types of random subselections you can choose from your original set of features. Keep in mind, the more features you have, the more likely a higher number of estimators or decision trees are going to be used and are going to glean more information for your model. But we can see here that after a certain number of trees, new trees are just going to be highly correlated or possibly perfectly correlated to older trees, meaning that while we are not overfitting to the training data, we are also not producing any more information, allowing us to hit that threshold. Now, luckily for us, this is a very powerful concept behind the random forest. The fact that you can actually be quite lenient in setting the number of estimators due to your hyperparameters, since overfitting is really of minimal concern. That means you can set it to some default value like 100 and later on perform a grid search to figure out where you should go from there, either slightly higher or slightly lower. But we don't have to worry about hitting some sort of perfect mark since we can easily overshoot that number of estimators and we would only be producing more trees that were correlated to historical trees, not adding too much information and not having to worry about overfitting. Now let's discuss how to choose the number of features to randomly select at each split. So this is known as the number of features hyperparameter in the random forest, which answers the question, how many features to include in each subset when splitting at a node. Recall that if we have some n number of features, we're going to select a subset when we're splitting at a node. So how many out of the total n should we choose? Well, in this case, we can take a look at the original publication for random forest, which suggested a subset of log base 2 of n plus 1 random features in the subset. So given a set of n total features, you would choose log base 2 of n plus 1 as the subset amount to choose from. And this is recommended from the original publication. Now, if we take a look at Leo Breiman's official page on random forest, he actually has a very interesting remark. He notes, quote, "An interesting difference between regression and classification is that the correlation increases quite slowly as the number of features used increases." So what does that actually mean in practice? This means that based off the supervised learning task we're trying to complete, whether it's regression or classification, we may want to adjust our default value for the number of features in the subset. We should note that the current suggested convention is to choose square root of n in the subset given n features. And later suggestions and publications by Breiman indicated that n divided by 3 may be more suitable for regression tasks, which ends up being typically larger than square root of n. Now, we should also note, Introduction to Statistical Learning, that is ISLR, indicates this should actually be treated as a tuning parameter, where you start with square root of n as a good starting point, and eventually do a grid search for a little bit less than square root of n or a little bit more than square root of n. As all the previous options shown were explored using empirical methods, it's extremely likely you're going to need to adjust based off your specific data set. That is to say, things like log base 2 of n plus 1 or square root of n or n divided by 3, those were all just explored through empirical methods, meaning they're not a set in stone convention that you shouldn't stray away from. Instead, think of them as starting points for your grid search, since it's very likely for your particular data set, you're going to have to optimize and tweak your hyperparameter slightly to try to squeak out a little bit of better performance based off the starting conditions for the number of features. And that goes towards the number of estimators to choose from as well. What we've given you is a set of default starting points, which you can choose to then grid search either a little lower or a little higher to try to get the best model performance possible. So as a review, for number of estimators, start with 100 as a default. Keep in mind that is currently scikit-learn's default value, and feel free to grid search for higher values. If you want to do a visualization of number of estimators versus error in order to see that particular threshold being hit, feel free to do so. But really, a grid search is probably the best use of your time there, since it's not really going to help you to visualize anything, to visualize number of estimators versus error. Now, for number of features for selection, we should start with the default square root of n and do a grid search for other possible values. Maybe things like n divided by 3 in case you're doing a regression task, since that was empirically found to be slightly better performing than square root of n or log base 2 of n plus 1. Keep in mind, these are just suggested default starting points. You will have to do a grid search for your own datasets. Now that we understand how to choose the best number of estimators and best number of features for the subset selection, let's move on to exploring bootstrapping an out-of-bag error, two key ideas when it comes to random forests. I'll see you at the next lecture.